I hope the reason why investment is a lower line than our output capital relationship is fairly self-evident for you. So think about if it was equal to it. What that would mean is we are investing everything that we are consuming, which would imply, we are investing everything that we are producing, which would imply that we are consuming nothing. In effect, we starve to death. That would be a foolish thing to do. Nobody's going to do it, and so that line needs to be at a lower level. Why is it the same shape? Well, assuming a constant investment rate, then if you think about it, it needs to have the same shape, but it's going to be lower down. So if you think about it in this picture here, we have an investment rate arbitrarily chosen by the book of 30%. In that case, it's going to be the same shape because it is 30% of the larger line. And so that's going to have the same shape. So this is one of the areas where people sometimes get confused, is investment is a function of the investment rate and output. It is not a function directly of capital, although we can rewrite it to be a function of capital. On the other hand, we're going to assume that a certain percentage of machines just break down every year. And that seems pretty reasonable. Now, we could make a richer assumption that the number of machines that break down every year is also a function of how intensively we use our existing machines. But let's make our lives easy. Let's set this up as it just being a certain number of machines because of regular wear and tear and the nature of physics and friction break down every year. In this case, the book has chosen 0.02. So 2% of machines break down every year. So now depreciation is a function of the depreciation rate and capital rather than investment, which was a function of the investment rate and output. So when we put these two lines together, we end up with the fact that they will, at some point here, at some level of capital, cross. Now, this point where they cross is what we're going to call the steady state. Now, the way the book has drawn this, I'm not wild about, because what we actually usually talk about is the steady state level of capital and output. Although we can talk about the steady state level of investment and depreciation. So here we have the diagram showing the steady state level of investment and depreciation. Of course, the whole reason we're using this is because at the steady state level of investment and depreciation, we will have a steady state level of output. And at that level of output, we will neither be growing nor contracting. So that's one thing for which we're going to use this. This allows us to say something about whether we expect capital to grow or shrink. Now, whether capital is going to grow or shrink depends upon, obviously, our investment rate and our depreciation rate and also our alpha. But for a given level of depreciation, so for a given rate of depreciation and a given rate of investment and a given alpha, it turns out whether our capital will be increasing next year or decreasing next year depends on where we are. So in this picture, if we are to the right of 225, in other words, if we have more units of capital than 225, let's go all the way out to 400. If we have 400 units of capital, 8 of those machines will break down next year because 0.02 times 400 is 8. On the other hand, and this is the case where we've redrawn, investment is only a function of output and the investment rate. But since output is itself a function of capital, in other words, y equals k to the 1/2, we can substitute that in. So in this case, 3% of output at 400, let's see what the square root of 400 is. My guess, it should be 20, right? Yes, 20 times 20 is 400. So when we have 400 machines, we will have 20 units of output. Of that output, we will set aside 30%. So we have 20 units of output. We're going to set aside 30%, which would be 6 units of machines added to the stock for next year. So we would be adding 6, and 8 will be breaking down. So what will happen is next year, we would only have 398 units of capital. Our stock of capital has decreased. What will also happen is our output will decrease. Instead of having 20 units of output, let me pull up my calculator quickly here and say 398, because that's the difference there. And the square root of 398, oh, come on. I can't get my calculator to turn sideways, but we'll set that to one side. Let me see here. Nope, can't pull that up. If you take the square root of 398, and I apologize that I'm not able to do that at present, you're going to get something less than 20. In other words, GDP per capita has decreased. So if we have more than the steady state level of capital, our capital and our output are going to be decreasing next year. On the other hand, if we have less than the steady state level of capital and less than the steady state level of investment and depreciation, we will be increasing the number of machines that we have next year. So if you look there to the left where they've nicely illustrated 100, when capital is 100, that means that we're going to have 10 units of output next year, which means we are going to save 30% of that output. We're going to have 10 units of output this year, of which we're going to save 30% or 3 units, which means our stock of capital next year is going to be 103. Except for the fact that when we have 100 units of capital, 2% of those units are going to break down, which means we're going to have depreciation of 2. So the net impact on capital is going to be 3 minus 2. So we're adding 3 and we're losing 2. So next year, our stock of capital would be 101. And we would have a higher level of output than we did this year. So the interesting thing about putting both these in here is that it actually allows us to say what will happen next. With just our capital output relationship, it is useful because we can exogenously change capital. In other words, from outside the system, we can just try moving that capital left and right and see what will happen to growth. Just in effect, like what I did with Germany and Japan, thinking about that. However, now we'd like to say, once we set up an economy and let it loose with these various parameters, this theoretical economy, what will happen across time? So, one of the big takeaways here is that when investment is greater than depreciation, what's going to happen? Capital will increase next year. On the other hand, when an investment is less than depreciation, this is not our investment level, by the way. This is our investment level, not our investment rate. Across that entire picture, that last graph, our depreciation rate was less than 1/10 of our investment rate. What we're talking about here, rather, is the amount of investment and the amount of depreciation. So when our amount of investment is less than our amount of depreciation, we are going to have fewer machines next year. And when our investment amount is equal to our depreciation amount, we will be stable. Now, I've drawn this. Obviously, going out to 100, we know that they're going to cross, given the parameter set up by the book at 225. So I'm going to zoom a little further out. So here would be the question. So there we go. We get them crossing at 250 or 225, depending on the parameters. And again, we should be able to think what happens. If the depreciation rate goes up, what's going to happen here? Well, our whole red line will shift up. We're still at, let's say we were at the steady state before. Now, this is going to be part of the difficult thing with some of these videos, and I want to get to the point where you know enough after these videos to ask me in the chat on Monday what examples you would like me to work through. We may even be able to do that in person on Monday. But we need to get far enough for you to figure out where your questions are. You need to understand mechanically how this operates. So if the depreciation rate goes up, our whole red line would shift up. And if we were at the dashed point in capital and output, I know that's not dashed, I should have drawn that over. But at that point, then what would now happen if our depreciation rate shifted up? Well, now the number of machines would be higher than the number of machines that we are adding. And so we would end up having fewer machines next year, which would mean our dot, if you think about that dotted vertical line, that would now move to the left. That would be our next year's level of capital, which would mean our output would be lower than it was this year, which would mean we would see negative growth. On the other hand, if we lowered the level of depreciation, the amount of depreciation, our red line would shift down. If we increase our investment line, that line would shift up. If we decrease our investment rate, our green line would shift down. Neither of these will shift our black line here. Neither of those will shift the relationship between capital and output. That black line is simply saying that if we have this much capital, we are going to have this much output. Our depreciation and investment lines, the red and the green, depreciation is the red, the green is investment, they tell us how we can think about how much capital we expect to actually have. Now, turns out there's something else. Say alpha changes and our black line moves up. Then by definition, if everything else stays the same, our red line would stay stationary, but our green line would move up. Why? Because 30% of a larger amount is a larger number. Okay, so you can certainly be able to play with some of these. I would encourage you to set this up in an Excel sheet and play with it. Then you can change some of the parameters and see what happens. There's an appendix in the textbook that talks about how to set this up in Excel, and I strongly encourage you to do so. That's one of the best ways to work with this and to understand it is to play with it. Now, every year, a relatively small portion of my students take me up on that, but the ones who do invariably both understand more how to use Excel, which is a good thing, but also how to understand and think about this model. So that leaves us with another question here. Hopefully you understand mechanically how this will work. I'm going to pause or stop this video and record another one here in a moment. But here would be the question: how long do you think it will take for us to get to the steady state? Now, a side note, I'm probably going to stop recording videos or stop putting the videos I'm recording in for the Monday class. I will put the others in for the Wednesday class, but I would encourage you to keep going. If you have time, it would be good for you to get ahead so that you can ask me as many questions so that I can have as much time to respond as possible. So how long do you think it will take to get to the steady state? You'll notice in none of the graphs that we've drawn so far was time on any of these axes. So I'll stop it there and we can pick it up in another video. Maybe see if you can commit yourself to a thought on how long it would take us to get to the steady state.